Thanks very much for the generous invitation to speak here and the introduction. So yeah, this is based on work with several other people. I'll mention them when I get to the. Yeah, so the problems I'm interested in to start with are, let's say you have a polynomial of degree d and also in d variables. I'm interested in kind of the values of this polynomial. So when the number of variables is the same as the degree, it's kind of a critical case where if an integer is represented, it's probably not represented many times. So it's kind of at the boundary. That's why it's maybe interesting. So let me begin with the case d equals 2. We've seen both of these results mentioned already in previous talks. So one is the number of integers up to x that are a sum of two squares is of the size x over log to the 1/2. With the constant in front found by Landau and separately by Ramanujan. And also, if we, instead of a squared plus b squared, we look at the split form a times b, but we still require a and b to be of size x to the 1/2, then the number of n that are represented is a multiplication table problem, and it's the most precise results due to Kevin Ford. And we saw that it's of size x over log x to the delta times the subtle log x to the 3/2 factor. Okay, so what happens if we go to from d equals 2 to d equals 3? Then it seems to be much harder, since most of the time there's no longer any multiplicative structure to rely on. But we can still ask these questions. So let's say we have like a, say, homogeneous polynomial p or cubic polynomial p. This I want to exclude some what Hardy and Littlewood called diminishing ranges polynomials, where you can kind of cheaply do this problem. So how many integers n are represented by this polynomial, cubic polynomial p? Let's say we put the natural height restrictions a, b, c should be at most x to the 1/3. So if, say, for homogeneous polynomials, I don't know any unconditional example where a positive density is known, but we should probably expect it for a generic polynomial. For example, sum of 3 cubes, that's a famous one. And then another one studied by Ghosh and Sarnak is the Markov polynomial, a squared plus b squared plus c squared minus a times b times c. Yeah, so maybe we expect a positive density, but it's hard to prove. But if you allow the variables to be a bit larger, then sometimes you can say a bit more. So for sum of 3 cubes, there's a clever linear construction over function fields. So you can take a, b, and c to be certain linear functions of n to solve this in most function fields, though that doesn't work over the integers themselves. That's due to Serre and Wasserstein. And for the Markov problem, this was studied by Ghosh and Sarnak. They got an almost all representation results under natural necessary local conditions. For a, b, and c going up to square root of n. So they can't quite take n to the 1/3, but they can do n to the 1/2. And that's by taking one of the variables to be small to make it look more like a quadratic equation. There's still a lot of subtle work to be done there. Okay. So yeah, so if say we're interested in sum of 3 cubes, then what's relevant is we can still try to prove statistical results, at least conditionally. And for that, we need to study, go into the circle method and vials, cubic Weyl sums, things like that. So let S alpha beta, so given any angle alpha on the unit circle, we can look at this exponential sum with cubic phase, e to the 2 pi I alpha x cubed. Say going up to the length of the sum is b, capital B. So classically, we have this b to the 3/4 Weyl bound, either done by Weyl differencing, or you can also prove it by Poisson summation and the ranges that are relevant for the circle method. So here a over r is like a rational approximation of the angle alpha on the circle. Don't worry too much about the specific ranges I put there, but it includes when r is around b to the 3/2, which is the most important for the circle method. Okay, so the important thing is classically we had this 3/4 exponent, and it seems hard to improve, but at least in some cases it can be improved. So if r has a convenient factorization, then Heath Brown showed that using Poisson summation and Q van der Kolk bit differencing twice, and then another Poisson summation, you can improve 3/4 to 5/7. And in the function field setting, there Weyl has some nice recent work we're using by bounding the singular locus of certain varieties. He was able to show that you can improve 3/4 to 5/8 in general. Okay, so the relevance of these Weyl sums is that you can express the number of solutions to, say, a sum of s cubes equals 0, where the variables go up to size b, as the sth moment of the Weyl sum. Okay, integral from 0 to 1, or integral of a unit circle of s alphabet b to the s. So the quality of the most basic approach is the quality of the Weyl sum bound determines the quality of the error term, or how small s can be, if you want an asymptotic for m, s, comma, b, the s moment. So let me just say for small values of s what is known. So in 3 variables, what you can say is, by using the divisor bound, the number of ways to solve x cubed plus y cubed equals n is at most b to the 1. You basically fix one of the variables, and the rest is a divisor bound. So b to the 1 plus epsilon. And it's open to improve this. Okay, and then in 4 variables, an asymptotic is known. The dominant contribution comes from linear or trivial solutions, where the variables sort of pair up to sum to 0. So, and then away from these lines, you can ask what's the best error term. That's the Monin conjecture, and then the best result is 4/3 plus epsilon. Maybe you conjecture 1 plus epsilon. This is using the geometry of the lines on the cubic surface to prove this kind of result, not the circle method. Okay, and then 6 variables. This is a famous open problem. So a classical result of Hua shows that the 6th moment is at most b to the 7/2 plus epsilon. And we only know how to improve it by a power of log. That's thanks to a work of Wang using smooth numbers, essentially. So if you want to improve this to a power saving, that's equivalent to showing that the worst case Weyl bound doesn't occur too often. So there's it's a specific large value problem near 3/4. Okay, and if I want to talk more about some other settings where you can do better. So for example, you can Woolley studied, for example, if you require the variables to be smooth, then you can do a bit better. I want to talk about conditional / function field results, where we have GRH available, and then we can push this further for M6, get near optimal or optimal results for M6. Okay, so in general, what is known about this point count from the, let's say, GRH conditional / function field perspective? So if, as before, MS is the number of solutions to this S variable cubic in a box, say S is at least 4, then by using clever geometric methods based on Mori's bend and break, as well as some Bezout type intersection bounds, you can show that there's a nearly optimal upper bound as Q goes to infinity of the b to the s minus 3. So if you wanted to push this further, it would require understanding proving certain homological stability results, which seems difficult to me, but maybe it's possible. I don't know. So of course, in number theory, we're familiar. Even if you have an upper bound, it may be hard to get an asymptotic, like for divisor problems or sieve problems, for example. Okay, so I want to talk more about the circle method approach, or its variance due to the ultimate symbol method due to Duke familiarity vignettes and built on by Heath Brown. So using the circle method, Hooley showed that if you assume standard conjectures for L functions of certain varieties, then you can get a near optimal bound, exponent 3 plus epsilon. I'll explain where these varieties come up later. They come from Poisson summation, basically. And then because we know all of these conjectures over function fields, thanks to Deligne's work, this can be made unconditional in function fields of characteristic, say, not 3. That was worked out by Jakob Glass and Leo Hochfilzer. And then it's natural to ask what you need to go remove the epsilon and get an optimal result. So in my thesis work, I showed that you can get the expected asymptotic formula. So this features 2 main terms. One as a new one is a product of local densities, which is familiar in the circle method. The other thing it new to comes from sort of special solution subvarieties. So like linear solutions where you pair up 2 of the variables to be 0. So you get both terms. You get both terms in the circle method from the circle method, assuming in addition to GRH the ratios conjecture and also a square-free sieve conjecture. So some connection to random matrix theory conjectures here. Okay, then in the function field setting, there's of course more hope to eventually prove unconditional results. So in particular, we can just the ratios conjecture by itself suffices there. That's joint work with Tim Browning and Jakob Glass.
Sorry, can you explain how ratios conjecture gets involved?
I'll get there, yeah. Yeah, and I'll also explain, I mean, by second moment / variance analysis, you can get statistical results on sum of 3 cubes once you know enough about the M6. I'll say a little bit more about that later. Okay, so what's the circle method context? This is 6 variables, cubic equations, what's called the square root barrier. The point is, MS is this nth moment of S alpha beta, S alpha B, and because S alpha B should generically be of b to the 1/2, maybe b to the 1/2 plus epsilon size, if we want an asymptotic, that means we're going to have to detect non-trivial cancellation essentially on the minor arcs of the circle method. So the point is we can't just take absolute values on S. We have to maybe hope to have some formulas that we can expand and actually push this analysis further. And that's what Poisson summation will let us do. So Vaughan observed that, I mean, classically the 3/4 bound was proved by Weyl differencing, but Vaughan observed that using Poisson summation, you can recover the 3/4 exponent again. And the advantage of Poisson summation is that it's actually, it's not just a bound, it's a formula. And you can try to push that formula further. And that's exactly what Hooley and later Heath Brown did. So they pointed out that you can get square root cancel, if you take the 6th moment and average over arcs, you can get square root cancellation over the numerator A mod R through Deligne's work. And you can get further cancellation over the denominator of the fraction R, or the modulus, through GRH, at least for generic, say, square-free moduli R. And at least heuristically, this shows that M6 is at most b to the 3/4 to the 6, and then -2 for the square root cancellation over A and R. And if you work that out, it's 3 plus epsilon. So that's a near optimal bound. There's a lot more work that goes into this. You have to think about things like small r, certain bad moduli r's, square-fold r, things like that. But maybe this is the rough idea. Okay, so let me be a little bit more detailed about where the GRH comes in. So the point is we have our cubic form in 6 variables, f of x, sum of 6 cubes. Yes? Sorry, which result for? The M4? M3 is just, this is the divisor bound. No. This is b to the 1 plus epsilon. Is it you fix one of the variables and use the divisor? Yeah. Yeah, but the point is the M6 bounds is a much better bound on average. Yeah, thank you. Okay, so yeah, in the circle method, what the point is, yeah, so when we apply Poisson summation, we're going to get some Fourier transforms, and that's where this, so we're going to get a family of varieties with this linear hyperplane section corresponding to the Fourier transform, f of x equals c dot x equals 0. And I'm going to explain this in the function field setting, so things are a little bit cleaner, but just pretend this is integers if you want. Okay. So the point is by Poisson summation, as basically along the lines of what Wang suggested, I guess, what you get is originally we have a sum of length where each variable is of length b, and we convert this to a dual sum. Our moduli are of size b to the 3/2 roughly, so we convert this to a dual sum of length b to the 1/2. That's the dual variable c. And we get a sum of exponential sums times complete exponential sums times oscillatory integrals, SC times IC. So let me not say much about the oscillatory integral, but the exponential sum, which is where the L function comes from, is and I'm going to square root normalize everything. So it's a sum over the numerators a mod r, and then the variables x1 through x6 go also mod r. So it's this Fourier transform. We have a times f of x plus the linear thing, c dot x, all over r. So this has 7, I guess, variables mod r, so square root normalization would be r to the 7/2 size. So this you can show, because f is homogeneous, you can show that this is a multiplicative function of r. So that's a good sign if you want to connect it to L functions. And it also behaves a bit differently at sort of generic primes where the varieties, hyperplane section is smooth versus not smooth. In the generic case, where the discriminant delta c is non-zero mod pi, then these exponential sums, if you form their local Dirichlet series, it's sort of approximated by the 1 over an L function associated to the variety the hyperplane section VC. So 1 over L, it could either be L or 1 over L. You have to do some essentially topological calculation to see which it is. It's -1 in this case. And okay, this is an approximation up to some, let's say, second order factor. So like if S is size 1/2, then the error term could be significant, like in Chebyshev's some Chebyshev bias type thing. But at least if S is bigger than 1/2, then this is a good approximation. Okay. So that's where the L functions come in, but I mean, I guess that was kind of the generic behavior. You also have to handle everything else. So this is the difference between what's called an Augusta zeta function versus Hassave zeta function. So they agree sort of generically, but not completely. And that can be subtle, so it's an extra complication. But at least morally, we would expect that these exponential sums SC are well controlled by the L function, or 1 over the L function. Okay. So yeah, as I said, you can use GRH to control the L function, or 1 over the L function. And we also have to handle the difference between, the Augusta thing and the Hassave thing. And that's some geometry that's controlled by this discriminant, delta C, which measures how singular things are, okay, essentially. And eventually, once you work out all the different contributions and balance them out, you get a near optimal bound of 3 plus epsilon. And there are several different sources of epsilon. Of course, one comes from GRH, but there are others, so for example, coming from these local errors, which I didn't say much about, and also coming from actually the dyadic summation. So each dyadic interval of R gives you the same contribution. So when you sum up, that's another possible epsilon loss. Okay, so yeah, as I said, since GRH is known over function fields, you get near optimal 3 plus epsilon unconditionally over function fields. That's Glassenhag here. And yeah, so if we want to remove the epsilon and go further, so let me briefly discuss some main term calculation first. So far I've been focusing on when the discriminant is non-zero. So that's when you can actually define the Hassave L function, and it means something in this context. if discriminant is 0, that turns out to be where the main term comes from, expected main term. So as I said before, first term is a product of local densities. The second term comes from special subvarieties, special linear subspaces. And okay, it's familiar where the first term comes from. That comes from c equals 0. Whenever you do Poisson summation, the central term is some kind of probabilistic local density thing. The second term is a bit subtler, and where it comes from is that whereas these square root normalized sums SC were kind of normalized to be generically of size 1, if delta c equals 0, they're typically biased to size pi to the 1/2 plus some error. And because this kind of main term pi to the 1/2 is a bit larger, and also it's independent of c, this can be thought of as some kind of conductor dropping phenomenon. There's no longer variation over c mod pi. And what that means is that this complicated oscillatory integral I didn't talk about, we can kind of replace it with some sort of average over linear space or something. And then that's much easier to understand, and that eventually that isolates the contribution from linear spaces to the point count. So okay, this accounts for the conjectured main terms, and then what we're left with is showing that the delta c not equal to 0 gives you an error term, so it's little o of b cubed or something. Let me first explain simpler, just removing the epsilon from that contribution. So we want to show that the sum over delta c not equal to 0 of these s times i's is at most, say, b cubed or little o of b cubed maybe. And we want to use the ratios conjecture. So let me explain. I mean, we saw the L function, so it's natural to see that it could potentially be useful here. Let me go into a bit more detail. So the point is, first we can show that the integral is kind of constant on dyadic ranges. So you can kind of not worry about factor that out and not worry too much about it. Then what we want to do is consider the sort of good moduli that are co-prime to the, or that divide the discriminant versus are co-prime to the discriminant separately, because as I saw, those behave differently. The ones that are co-prime are modeled by the L function. Okay, so the point is, in the Glass and Hochfilzer work, they show that this dyadic sum sigma b n0, n1, when you fix the dyadic sums of R0 and R1, this is of size b to the 3 plus epsilon. And then the point is, if I define this parameter n infinity, so that n0, n1 times n infinity is b to the 3/2, then what we show is that we can remove the epsilon and then also get a power saving in the n0 and n infinity aspects. So those used, yeah, so the point is, if n0 and n infinity are tiny, then the problem is well approximated by L functions, and then we can use the ratios conjecture. If n0 and n infinity are large, we need other ideas. So n infinity is kind of based on some oscillatory integral estimates involving cancellation over arcs in the circle method. That's yeah, okay, I'll be more precise. Yeah. I mean, we already saw the family of L functions. I'll explain exactly what the ratio conjecture says here. Yeah, so there are these other two aspects. Let me briefly explain where, say, n0 comes in. So the point is, yeah, so we need to make sure that n0 is kind of not too large. N0, these bad sums are not too large, usually, so that they don't interfere with the L functions. So yeah, essentially what we show is that the probability that it fails, fails square root cancellation badly is kind of small. And that actually crucially relies on the fact that we have a cubic form and not a quadratic form. So the fact that cubics are kind of more random than quadratics. Okay, I mean, yeah, there are lots of other technical ingredients. For example, we need square root cancellation for certain singular varieties, not just the smooth varieties given by the Weyl conjectures. But okay, the upshot is we can kind of, we get this some power saving in this aspect. So yeah, so the ratios conjecture is used as follows. So the point is we had the sum over good moduli, and then its Dirichlet series can be well approximated by now we want something that's not just a good approximation for a real part of S bigger than 1/2, but even on or a little bit to the left of the critical line. So we need not just 1/L, but also some polar factor, say P of S, which is essentially some product of zeta functions near the line 1. So yeah, so you can prove that there's a good approximation of this form. And then the ratios conjecture that we use, for example, is essentially we have a bunch of 1/Ls in the denominator. So there's no L's in the numerator, just the denominator. We want to evaluate averages of 1/L over our family of L functions. Okay, and this has some random matrix theory factors like the zeta S1 plus S2, and there's also an arithmetic factor A of S1 S2, which essentially of size 1, so it's pretty mild. You can basically ignore it. And then we want some, say, power-saving error term where beta is fixed. So the point is we're interested in not the full L function, but just like some dyadic pieces of it. So if we multiply by n1 to the S1 plus S2, and then do some contour integral, then where the real part S1 and S2 are 1/2 plus beta, then since n1 is at most b to the 3/2, eventually you get, by contour shifting, that, the contour shifting will kill the zeta factor when you shift S2 to 1 plus minus S1. So you won't get any logs when you do this. And that's important. Okay, so yeah, this is the idea for how the ratios could actually come into play. Yeah. Okay, so in summary, yeah, assuming, for example, the 0, 2, 2 case of the ratios conjecture for this family, you can show that you can remove the epsilon, so you get to the upper bound of b cubed, and by essentially Cauchy-Schwarz or second moment method, this implies that sum of 3 cubes equation is soluble, say, in the smallest height you could hope for a positive density of n. So I mean, Wasserstein did it when x, y, and z are of size n, but now it's of size much smaller, so it's harder to solve. Yeah, this is a positive density results, and with the constraints here, you can't actually get density 1, but if you allow your variables to be a little bit larger, not just exactly degree 1/3 n to the 1/3, but maybe n to the 1/3 plus epsilon, then you can get density 1 of n's are represented in this form, so it's nearly optimally. So yeah, again, this is assuming the ratios conjecture, or I mean something a little bit weaker than the full strength of the ratios conjecture. But anyway, yeah. So to get, I just explained what you need to do to get the optimal upper bound without the sharp upper bound without the epsilon. But yeah, pushing the methods a bit further, you can get an asymptotic formula, new one with the expected main term featuring the particle densities and also the linear subspaces. And that's what you need essentially to get to do some kind of variance analysis to prove a density 1 result for representing sum of 3 cubes. Yeah. So let me just emphasize that this uses ideas of many authors. So for example, Ghosh, Sarnak, Diakonu for the variance analysis. I mean, Ghosh and Sarnak did the Markov case, but so the idea is basic structure transfers to sum of 3 cubes. As I said, the Hooley and Heath-Brown's work on the circle method was where we started off here. The work of Beauville was essential for getting this conductor dropping kind of phenomenon on delta C equals 0. And then, as I said, the fact there were these like extra polar factors and the approximation to L functions. That's similar to what happens in, for example, Chebyshev's bias, as studied by Rubinstein and Sarnak. So the contribution from prime squares, things like that. Yeah, and then I mentioned, there are these other aspects like the n0 and n infinity, and for example, n infinity that uses essentially work of Jingjing Huang on rational points near manifolds. So it's like a purely real analytic kind of thing, where we needed extra cancellation on the oscillatory integrals over the arcs of the over the minor arcs in this circle method. Yeah, we also use stuff like Ekadal's sieve, square-free sieve of Kunin, which is unconditional in function fields. That's one advantage of function fields. Okay, yeah. Anyway, that's the rough idea for the sum of three cubes and the 6 variable cubic thing. So I want to talk about something more recent, which is joint with Browning and Munshi, where we try to still look at 6 variable cubic equations, but maybe change it a bit, make it a little bit easier so we can try to get like an unconditional asymptotics, but still essentially at the square root barrier in the circle method. So the equation we'll look at is like with this x1, y1 squared plus x2, y2 squared plus x3, y3 squared equals 0. So this is no longer a smooth thing. It's singular along the plane, y1 equals y2 equals y3 equals 0. And yeah, so we can think of this as maybe some kind of deformation of 6 equals 0. And it turns out that L functions are not going to play the same important role that they did for the Fermat, but instead we're going to get some divisor type problem involving, I mentioned some discriminant polynomial delta C for the Fermat, the 6 variable, sum of 6 cubes equals 0 thing. And here, there's a simpler discriminant polynomial, which is of degree 6 instead of 48. So it's I have the formula written down here. It's with this polynomial GMN. And basically, we need to know, at some point, we need to know that the divisors, the balanced factorizations of this polynomial GMN in certain dyadic ranges. And that's controlled by what's called the Hooley delta function, which is useful for saving powers of logs, things like that. So yeah, let me say a little bit more about how this comes in. So in general, if you have a sort of say 6 variable cubic form, or in general, you can always form some discriminant variety by looking at the Gauss map, and this image will give you the discriminant. And the kind of degree of the dual or discriminant is kind of a measure of complexity or like curvature somehow of the variety of the problem we're interested in. So here are some examples. So maybe the first example was done by Botrev, Chinkel, and Selberger. So it's a toric variety. So if you take with multiplicative structure, so x1, x2, x3 equals y1, y2, y3. So you can count points on this up to some given height b accurately using multiplicative harmonic analysis, or essentially products of zeta functions, or using universal torsors. And this is an example of a self-dual variety, where the dual variety has degree 3, so the same as the original variety. Another example was studied more recently by Blomer, Brudern, and Selberger. So it's essentially a sum of 3 fractions equals 0, then you clear the denominators. You get this x1, y2, y3 plus ... equals 0. Again, that's a self-dual thing, and they again used some torsors and lattices to count this. And another recent example by Derenthal is if you're interested in counting symmetric 3x3 matrices whose determinant is 0, that has some geometric interpretation in terms of the Veronese surface. And there, you can also count points using a result of Schmidt. And this is the degree of the dual variety here is 4. In our example with the xi, yi squared equals 0, this example is, I guess, more complex. Has a degree 6 dual variety. And then maybe the hardest is what I started originally with, the sum of 6 cubed equals 0. That has a dual of degree 48.
In 3, what is the geometric reduction?
Schmidt counted points on, like, quadratic points on projective planes or something like that. So symmetric Gurov planes. So there's some reduction like that. Yeah, thanks. Okay, so Yeah. So yeah, let me also mention that I guess since this equation has a lot of extra like linear and quadratic structure, I mean, it might be possible to, we're interested in doing it through the circle method where there's a square root barrier, but it might be possible to do it by other methods. There's a whole industry of playing off linear and conic bundle structures. So let me mention some of the results in this industry. So for example, Budek got, I guess, matching upper and lower bounds for a related counting problem on the same variety with a anti-canonical height and Monon's conjecture. Browning and Heath-Brown did like kind of the 4-term version of this, combining lattice methods with the circle method, depending on whether x or y is bigger. And then in Baynard's thesis, he treated a sort of higher degree version of this, but you need more variables. Okay. But yeah, I want to focus on the circle method, and here there's, I guess, some a geometric phenomenon that comes into play. So we're interested in these kinds of Fourier transforms SC in the circle method. And yeah, let me just write that a little bit differently. So if we have say, absolutely irreducible polynomial f, and we're interested in its Fourier transform TCP modulo various primes p, then by Plancherel's theorem, the second moment of this Fourier transform is the size of the density of points on the variety f, so which is roughly 1 by the Langevin estimate. And roughly speaking, in practice, there are 2 kinds of things that can happen. Let me just informally call them the focused and balanced cases. So focused case is when there's a subvariety on which the large values of the Fourier transform concentrate. So we know the whole second moment is 1. So focus is if there's a subvariety where even if you strict to there, you get most of the second moment. The other case, let me say, is the balanced case. It's where that doesn't happen on no matter what subvariety you go to. The second moment is decays a little bit, say by a factor of square root p. And here we see the difference between the 2 examples, the sum of 6 equals 0 versus the Perazzo type thing. So the Perazzo type thing turns out to be focused, whereas the sum of 6 cubes thing turns out to be balanced. So concretely, the way we should get focused is that most of these sums will have better than square root cancellation. So here I define t with a hypothetical square root cancellation, but actually typically in the focused case, t is little o of 1. In fact, it's big O of p to the minus 1/2. So you get an extra saving there, and that essentially comes from the linearity in the x1, x2, x3. On the other hand, in the classical sum of 6 cubes equals 0 case, that doesn't occur. It's more balanced. So when you put this in the circle method, what happens is that in the focused case, the singular primes turn out to be more important than the other primes, whereas in the balanced case, the primes that don't divide the discriminant turn out to be more important. And that's why L functions played a big role in the latter, but not the former. And this is also connected to something Katz called the A number. So essentially the A equals 0 corresponds to like some better than square root cancellation. And that's the focused case. And then A not equals 0 is more essentially more balanced. Okay, so where this comes in the circle method is, again, we're interested in the same kind of dyadic sums that I defined earlier, where you have the integral and then a product of contributions from singular moduli and good moduli, R0 and R1. And this time, you don't need GRH or anything. You can already get relatively easily just by like divisor bounds, things like that, get b to the 3 plus epsilon. So, and then again, if you let n infinity be this complementary size modulus, then what we get is b cubed times log b to the epsilon with an extra saving in the n1 and n infinity aspects. So the log b to the epsilon comes from some Hooley delta function type thing. If you just use divisor bounds, the best you could hope for is just log b rather than log b to the epsilon, but you can get that down to epsilon using more sophisticated methods by like Tenenbaum, for example. And then the log n1 comes from essentially from the prime number theorem. So as I said, we had this kind of better than square root cancellation, which means instead of worrying about L functions near the critical line, now we're just interested in L functions near the line 1, which is much easier. So there we just use the prime number theorem to get arbitrarily large powers of log saving, for example. Then n infinity is the same thing that happens for the Fermat case with sum of 6 equals 0. We get some cancellation over arcs using this work of Jingying Huang on rational points near manifolds, things like that. Okay, and if you sum over n1 and n infinity, these are dyadic parameters, you just get left with b cubed to the log b to the epsilon. And the reason this is good enough for an asymptotic is because in this case, the main term is not just of size b cubed, but b cubed and log b. There's an extra log from the singularities.
It's typical when you're using the delta.
Yeah.
You don't have the next term?
So if we wanted the next term, then I think the relevant problem is essentially some kind of balanced factorization problem. So we want to know how often the dual variety is divisible by some modulus R0 of size b to the 3 halves. And you can think of this as, so the difficulty is the divisor switching trick doesn't help you here. If you switch, you get the same size of modulus. But we can think of this as counting balanced factorizations. So factoring this discriminant polynomial into a times b of the same size. So this would be easier if G had degree at most 5, this would be an easier thing because you could do divisor switching to reduce the modulus. This seems like so this is, I guess, maybe if you're clever enough, you can squeeze out log or log-log saving in this problem. But yeah, I don't know. But maybe it's something interesting. Alternatively, it could be something interesting to look over function fields or something.
Can I ask something? Because I'm not really understanding the plan here. So
Okay.
2 slides back, you had focused and balance.
Yes. Yes.
And my guess is what you mean is that if you have the first line for focus, it also means that if GC is not equal to 0, you've got asymptotic 0.
Yes.
So all the weights.
That's what I was saying about we get sorry. That's what I was saying about the fact that we have a zeta function near the line 1 instead of the line 1/2. That's from the extra cancellation when p does not divide g.
In this calculation.
Yeah. Which.
Well, for this theorem you just proved.
Yeah.
You assume it's focused or the variety.
So it is you can prove it's focused in this. Yeah. So that's the reason I made this definition to contrast the two cases. In the original case we looked at, it's balanced. In this new case with xi yi squared, it's focused.
So your first term is essentially the focus stuff gives you a main term like the diagonal. Now you're saying the secondary term would come from other non-focused terms? I'm very mystified.
So I guess what focused means is that the contributions from this modulus R0 matter more than the contributions from R1. That's all it means. Okay, you're asking where the b cubed log b term comes from? I mean, that comes from the central term I didn't explain that. That comes from the central term m equals n equals 0 in Poisson summation. Here I already cut to g not equal 0, so I already exclude that. So the main term comes from c equals 0, which it's just
Super diagonal terms, the rest is error term,
yeah. So now this is just bounding the error term. Yeah.
Sorry.
Yeah, no. I know I'm skipping a lot here. Thank you for asking. Okay. So Yeah, so I just wanted to discuss that balance versus focus to contrast the types of behaviors that can occur. So you really have to look at the geometry. Okay, so now I want to go back to L functions a little bit and also connect to what, John mentioned in his talk, the recent homological stability developments over function fields. And that's, I'm not saying I know how to do the ratios conjecture for the family for the circle method at this point, but there's also another a simpler geometric family where there has been very definitive striking progress. So that's what I want to discuss a little bit. So this is the family of quadratic Dirichlet L functions over a function field. So let Q be an odd prime power, and let mu be the function field version of the Mobius function, and then let chi d be the usual Jacobi symbol, conductor D. Then what the Peterson et al. Showed. They resolved essentially the moments conjecture for arbitrarily large moments as long as Q is large enough in terms of the moment that you take. But I have a thing on the archive showing that, in fact, you can also say quite a bit about ratios, not just moments. So for example, you can get cancellation in arbitrarily sparse ranges of moduli R relative to the conductor D. So some power saving. For example, corresponds to the first 0-1 case of the ratios, so just 1/L. And also, if you look at you can also look at the 1-1 case of the ratio conjecture, which corresponds to looking at one-level densities, like in Phi's talk. And then using that, you can get an approximation to Chala's non-vanishing conjecture for the L functions at the central point. So you don't quite get that they're almost all non-zero, but you get a density closer and closer to 1 as the function field Q goes to infinity. Okay, and then, maybe I should say that on this non-vanishing stuff, there are also other methods from arithmetic statistics over function fields that have treated other cases, but this is at least new if Q is a prime that's 1/4. Okay, so let me briefly try to go into some of the methods here. So the first step is similar to what appears in work of Bump and Gambard verifying the ratios theorem for random matrices. So the point is we start as in the ratios recipe of CFK or S, and also with Zierenbauer later. And for all the L's functions in the numerator, you expand them using the functional equation. But then the point is, instead of directly working with Dirichlet coefficients, we expand everything in terms of zeros, or in the random matrix case, that would be in terms of eigenvalues of the matrices. And then we take into account what family we're working with, like unitary, symplectic, or orthogonal, and then break it into irreducible pieces. The advantage of doing this is that it'll be clearer to see where these various kinds of polar terms arise on the right-hand side of the ratios conjecture, or ratios theorem. And then after this step, then it kind of diverges a bit for the number theory versus the random matrix theory. So in the random matrix theory setting, what happens is that you have these symplectic Schur functors, say, and then only the trivial representations will survive the averaging over the random matrices in the random matrix case, once you decompose it into Schur functors. What happens in the number theory cases, it's not just the trivial representation, but maybe all representations of small weight relative to the family N will survive the averaging. The exact formula is a bit subtle. That's computed by this stable homology work of Bergstrom, Diacono, Peterson, and Westerlund. But actually the main point is that it stabilizes. And the fact that it stabilizes means that you can get some kind of, that's the same kind of limiting process you use to define the arithmetic factor in the ratios recipe. So the point is this homological stability verifies the ratios recipe, at least to some extent. Okay, yeah, so more precisely, once you decompose into irreducible pieces of, according to the representation theory, we have a sum over FQ objects. That's the family of L functions. But you can't really do geometry with FQ directly. We are supposed to think of FQ as the Frobenius invariance of FQ bar. And then, so that's what the Lefschetz trace formula lets you transfer FQ stuff to FQ bar stuff. And then you can sort of cut off most of the homology groups using Deline's bounds and certain exponential Betti number bounds. And what you're left with is proving a homological stability results in a linear range of homology groups uniformly over the local system with the symplectic shear functor. And as I said, so yeah, the arithmetic factor comes exactly from this stabilization. The fact that it stabilizes means it essentially corresponds to the limiting process that you use to define the arithmetic factor in the ratios recipe. And the random matrix theory factors come from the fact that we decomposed into irreducible pieces. Okay, so let me connect this more broadly to something that appeared in an interview with Atiyah and Singer. So Atiyah was like, physics is going to solve all the problems in number theory, you know, RH and so on. Singer had a more measured take, but which is I find interesting given the theme of the conference. He said that he predicted that a new subject of statistical topology will develop, where rather than we care about specific, topology and variance, we care more about the distribution. That's I think very closely related to these recent developments in homological stability. Where the monodromy group plays the key role of understanding the distribution and stabilizing and so on. So so the hyperelliptic curves, or the quadratic Dirichlet L functions correspond to hyperelliptic curves, and another way to think of hyperelliptic curves, which I like, is that you can think of those as hypersurfaces of degree 2g and weighted projective space G11. And okay, then you can see that maybe there could be other natural families to look at. For example, smooth hypersurfaces of degree tending to infinity in a fixed projective space, or smooth hypersurfaces in, say, some biprojective variety. The example 3 corresponds to what you would need in the to make the my work with Browning and Glass unconditional. So for sum of 6 cubed equals 0 in the function field case. These can all be thought of as some kind of hypersurface families. So more explicitly, the way the first thing corresponds to hyperelliptic is you write out the equation, and then there could be a linear term, you remove that by completing the square, then you just get the hyperelliptic curves. And then the way the third thing corresponded to the family of L functions I started with the talk with is the bidegree n, 1 just means you have some binary n degree n forms, binary form C Tu times xi equals 0. So those are the hyperplane sections. So what are the local systems that are relevant? So there are, 2 natural kinds, both of which appeared in this talk already. So we have these families of varieties, y sub f, say, and then there are kind of 2. So one local system you could look at is looking at the homology of the varieties yf. For example, h1 of the hyperelliptic curves that will correspond to the L functions of quadratic Dirichlet L functions. Similarly, you can get the L functions that for the varieties that I started the talk with. On the other hand, if you are more interested in like divisor type statistics, like for the second equation that I talked about with Browning and Munshi, then the local system would be more like a bit more discrete and combinatorial. You look at a certain permutation cover associated, and then the sort of permutation action on the cover sort of governs the whether you're what balanced factorizations, prime values, things like that. You can do any polynomial that way, in principle. So okay, let me So let me briefly say a little bit more. I mentioned you need some Betti numbers for the Lefschetz trace formula to go through. And you also need some kind of inductive argument to extract the arithmetic factors and so on, and get everything working. So that corresponds to some gluing maps. You also need some braiding to represent to sort of glue together the different ways, relate the different ways of putting one space into a bigger space. And then you also need a monodrome representation from your space to some arithmetic group to set up some comparison of their homologies. And you also need some automorphic representation theory, essentially Matsushima's formula and later work by Burrell, Vogen, Zuckerman, and so on, to compare a discrete homology of a discrete group to a real group, which is easier to understand. Okay, so the reason, so the point of gluing is that, or the induction is that if you want to show stability, you could also think of that, which is not necessarily a universal thing. What's more universal is the derivative vanishing. So 0 is a very universal thing. And if you try to do some induction argument, what you find is that you need the braiding for it to work. You need different orders of inserting objects. And you can even give counterexamples where you don't have gluing but not braiding, where the homology groups don't stabilize. So the braiding both gluing and braiding seem to be essential to this approach. Finally, let me mention maybe some modest progress on more general families. So you can prove exponential quality Betti bounds using Dwork theory, cover theory, and Stirling's formula. And you can prove. So this is exponential, yeah. The enemy is in Dwork's. At first, it looks bad because you have n to the n in the Dwork theory, but you're dividing by n factorial since you don't care about the order of the roots. Yeah. Okay, and then also you can define some gluing maps, at least say for homogeneous polynomials with constant coefficients, like the examples I discussed in this talk. And this is based on essentially Rouché's theorem. So if you take, if you multiply two square-free polynomials, the product might not be square-free because they might have a common factor, right? But if you push those polynomials to infinity first and then multiply them, then you still have a square-free thing. That's the point here. So that you do t plus epsilon inverse. The epsilon goes to infinity. You can also do a braiding essentially by rotating between t and t plus epsilon inverse to swap them. So okay, that's all I wanted to say. Thank you very much.
Thank you, Victor. Any question? Yeah, Andrew?
Way back. Proved basic result. Sums represent almost all answers with degree being exactly the same as the degree of n to the 3, which gives you very, very little wiggle room. So just simple question, do you have the number of representations?
So I mean, the variance analysis will give you like some kind of Hardy-Littlewood prediction on average holds.
Are there local factors?
Yeah. So there's some local factors.
Okay.
But that will only work if you allow yourself a little bit of epsilon wiggle room. The exactly 1/3 you don't.
Taking your exact result, it's so strong.
Yeah.
But so you can prove, but you can't get any. Can you get low bound estimates of representation?
You're talking about the exact 1/3, not 1/3 plus epsilon. No, that's just lower bounds. It's just a Cauchy-Schwarz argument. You can get a lower bound on the proportion, but it's not going to be optimal. No, but he was asking about not 1/3 plus epsilon, but 1/3 exactly. where you can only hope for positive density.
Not deformonic, that's clear. You've got to
Oh, no, okay, but even with non-monic degree exactly 1/3, you can't get all, or you can't get density 1. You can only get positive density. If you do 1/3 plus epsilon, then you can get almost all, and then you can also get an asymptotic almost always.
Good question, Max?
Is there any hope, or what's the main issue to generate this topology method to the version of ratios?
Well, I had 9 things I mentioned here 3 of them say. So I mean, I'm working on it, but it takes time. Yeah.
And James, you had a question?
I'm not sure I passed the quantification for the homological stability. So you were saying
Okay, yeah.
the degree n is larger than a constant times k.
So
Then you get your stability.
So this is, as long as you're in some sufficiently small linear range, then you can, of k's relative to n, then you can get uniform homological stability. This isomorphism holds.
Constant depends on what?
This is an absolute constant. Yeah, so it's independent of lambda, which is essential. Yeah.
Right, I think it's a good time to stop. So thank you, Victor, again.